In the last class, we saw something about negative feedback and how negative feedback can result in wideband amplifiers. We started discussing with the single stage negative feedback amplifiers how these single stage amplifiers can result in Y feedback and Z feedback amplifiers, negative feedback amplifiers possible only in Y and Z feedback, and how this can be cascaded to realize wideband voltage controlled voltage sources and current controlled current sources. Now, today we will see another basic principle. We would like to cascade one common emitter amplifier with another common emitter amplifier. That means two stages. So, consider instead of one stage that we have considered earlier, two stage amplifiers. See, we have a single stage amplifier being cascaded with another common emitter amplifier. This is the AC picture. Now, obviously, the loop gain can be enhanced considerably by cascading those stages. The disadvantage being, now the time constant involved in these two stages, minimum number of time constants that will figure in the gain, will be 3 instead of the 2 originally present. And therefore, there will be difficulties in giving negative feedback and sustaining a stable configuration, because the order of the system has already become 3 and the loop gain has increased. So, it is likely to become unstable. Therefore, we have to be very cautious in using this with high loop gain. It is highly likely that this is going to become unstable. Let us see. Now, however, because of its great advantages of desensitizing the performance factor with respect to active parameter, we would like to go for more number of cascading, cascaded stages, so that the loop gain becomes large. Now, in this configuration, we have two possibilities of negative feedback. What are they? H and G. Obviously, Y and Z will be positive feedback configuration. So, let us consider the negative feedback configurations which we have perhaps studied in our undergraduate days. H feedback, output voltage is that is output voltage is sensed, and fed back in series as voltage. It is called voltage series also otherwise popularly. So, we have the feedback resistances being called as RE1 and RF. Now, H feedback, it is easy to use H parameters in the analysis, because H parameters of the amplifier and H parameter of the feedback, this can be easily evaluated and added together, and the modified parameters will be the G parameters, and obviously all the G parameters except the forward transfer parameter will go towards 0. It is an idealization towards a voltage controlled voltage source. What happens obviously is that as far as the forward transfer parameter is concerned, it is going to become desensitized with respect to the active parameters and will become purely dependent upon the passive parameters, with the resultant effect for that particular forward transfer parameter, it is a wideband configuration. For that particular forward transfer parameter, it is going to be a wideband configuration. So, voltage controlled voltage source is the idealization to which it goes, and therefore, V naught over Vi is the parameter for which it is showing wideband effect. And the bandwidth is going to be enhanced by a factor of the loop gain by the same factor by which all the other parameters are decreased and made to go towards 0. So, this configuration in a simple analysis we can say that V I is the input voltage is going to almost entirely occur across RE1. So, V I by RE1 is the current, and this is almost entirely the current through the RF, okay, and therefore, this current into RF is the voltage drop across RF, and the voltage at the output V naught is going to be original V I plus the drop across RF. So, with the resultant effect, the voltage gain is going to be RF by RE1 plus 1, which we have analyzed by variety of means in our undergraduate days. This can be also analyzed in terms of purely H parameters and G parameters, and you will obtain the same value. The input impedance is going to be increased by the extent of the loop gain. The output impedance is going to be decreased by the extent of the loop gain, and it is going to become a very near ideal voltage controlled voltage source with a gain linearly equal to 1 plus RF by R. This is a popular voltage controlled voltage source wideband amplifier, which has been used in integrated circuit quite often. Obviously, for biasing purposes, we have to either do, if we are using all NPN, obviously in older technology, since we preferred only NPN devices, almost all wideband devices ICs used only NPN transistors, no PNP transistor was present. But in a technology where both good NPN and good PNP are present, we can sort of get over the problem of cascading and biasing by coupling these together. Okay. So, that is why you see in most of these configurations only, these are all old wideband amplifiers, only NPN transistor is present, because the PNP is a bad PNP with a bad frequency response characteristic. And also you will notice that since the time constant has to be made very low, okay, in order to make the amplifier wideband, the resistors used are all of the order of kilo ohms and hundreds of ohms. This is a characteristic feature of all high speed amplifiers, comparators, Schmitt triggers, anything that you think of in terms of integrated circuits, okay, where we design comparators, high speed comparators or amplifiers, wideband amplifiers or logic circuits, we must use low valued resistors and be happy with low value of gain. Now, in order to convert this configuration, if you want, I would like to fabricate this as an IC, therefore, I want to make my job of biasing easy, then I can convert this into what is the basic principle? Differential mode, right. By converting this configuration into differential mode, by converting every discrete circuit configuration into differential mode, you are getting over the problem of biasing, stable biasing. Okay. That otherwise would have required level shifting and also bypass capacitors, etc., etc. So, this is what is tried here. You can see this is one of the commercial integrated circuits fabricated using this kind of H feedback. I have just merely repeated exactly identical stage here. You can do the same kind of analysis that we did while converting a differential configuration. You can do that here. Just simply repeat the configuration here. then convert every one of them into what? Differential mode by introducing current sources or common emitter resistors. In this particular case, these differential configuration has been achieved by lifting this above ground and putting a common emitter resistance, okay. And also here this can be connected to ground, or in this particular case it has been connected to what? This is connected to plus, this has to be connected then to minus. So this is the DC picture. See how simply the circuit gets transformed into an integrated circuit once you have the basic feedback configuration with you. So if you see this configuration, it is nothing but essentially this configuration. Do you follow this? How that can be synthesized simply by adopting the configuration, the basic configuration, and converting it to differential mode by simply lifting the ground, okay, to a common point where the common emitter resistance or the current source is connected, okay. And the current source in turn can be connected to negative or ground depending upon whether it is dual supply or single supply. So this is the wideband IC which is making use of H feedback. But what we will see when we design such a circuit is invariably, if it is designed well, if it is designed to have high gain, high loop gain, it will go into oscillations, because all the three time constants, the input time constant, output time constant and the intermediate time constant become comparable to one another, and therefore in the region of interest all the three time constants come into picture, causing instability for the negative feedback. So how to make it become stable without losing bandwidth? Now this is normally done, unlike the case of op amps and others, where we are not so much bothered about the bandwidth, where we are bothered about its use in low frequency configuration as operational amplifier for mathematical operations of addition, subtraction, integration, differentiation, etc. There it may be used in a variety of negative feedback configurations, and therefore we would like to make it work for all negative feedback configurations. So the compensation adopted is dominant pole compensation. What it means is simply increase one of the three time constants so much that the gain reduces drastically within the frequency band, that when the actually other poles come into picture, the gain has already fallen to a value less than 1. So there is no question of the negative feedback turning itself into positive feedback at any particular frequency. This is by drastically cutting down the bandwidth. This technique is not at all suitable for wideband amplifiers with negative feedback. I have already pointed out that negative feedback should not be used if it is possible at all. If you want to design wideband amplifiers, we had seen those pairs where no negative feedback is used, but it will give the maximum bandwidth and gain bandwidth product. But these are not such configurations. The single stage is one configuration where it is possible to sustain negative feedback without causing frequency instability. But these two stage configurations are not at all like that, and invariably they go into oscillations. And how do you prevent oscillation? Now, to prevent oscillation here, what is adopted is not dominant pole compensation, it is pole zero compensation. That is, I will introduce a 0 to cancel out one of the 3 poles, but I should ideally introduce a 0 to cancel out one of the 3 poles, so that it becomes a second order system. But in the process of doing it using a capacitor, I cannot but introduce another pole. Okay? But this pole that I am going to introduce is going to be coming to picture at a very high frequency, so it is of no consequence, and therefore you can consider for all practical purposes that this pole zero compensated amplifier is essentially a 2-pole configuration rather than 3-pole configuration. Is this clear? That is called pole zero compensation. And where do you introduce this 0? It is normally introduced, if you see, the feedback resistance is nothing but RF the dominant pole compensation is called lag compensation. Okay. What will you call the zero compensation? Lead compensation. Okay. So, pole zero compensation is obviously lead lag compensation is the other terminology used. So, how do you therefore introduce the capacitor? Lag compensation is going to result in, if you put a capacitor across Re, there will be a lag between output voltage and, that is between the feedback voltage and the output voltage. If you want this to lead slightly, what will you do? You will introduce a capacitor across RF. This is something which you have been calling as speed up capacitor in the case of digital circuits. Okay. This will link the high frequency component very quickly with the feedback terminal. Okay. So, this is a lead lag compensation. This is going to result in a pole. Where will it result in a pole? What is the pole? A simple way of finding out this pole is simply find out what is the effective resistance across the capacitor that will come. Okay. If you consider that this is driven by a voltage source, okay, the pole of that configuration can be simply found out by finding out the effective resistance across the capacitor. What is it? It is going to be, if this is CF, CF into, so that is RF parallel RA, right? RF parallel RA. Where will be the 0 located? That also is visible very clearly. It is the resistance that is directly across CF, that is RF, RF parallel CF. Okay. So, you can locate the 0 at RF parallel CF, okay, 1 over RF parallel CF. RF parallel CF is the time constant, okay, and cancel out one of the 3 poles. In the resulting configuration, now we will have an additional pole coming into picture, which is having a time constant which is CF into RF parallel RA 1. So, which means actually now since the RF parallel RE1 can be made a low resistance, this is a low time constant and this can be located farther away from the region of interest. Okay. If this facility is not so easy, you can actually split RF into RF1 and RF2. Okay. RF1 plus RF2 being the actual RF needed for the low frequency gain, okay, and RF1 is the one that should locate the 0 at the appropriate point. Okay. So, this is what is provided externally by you, and the IC manufacturer will not, okay, give this capacitor or even suggest it. So, what you normally do is you will put just the value of capacitor that is needed to prevent oscillation. So, one way of doing it is practically simply observe the output, okay, see whether it is going to oscillations at all conditions of supply voltage and temperature. Okay. If it is going into oscillation, then increase the value of capacitor just enough so that it is eliminated. Just put a little bit more than what is needed. Okay. So, this is a practical way of stabilizing this wideband amplifier and also obtaining the maximum possible bandwidth for your usage. Okay. So, this is the compensation that is normally adopted for this kind of configuration. You see, already we are getting into problems, that the IC might give you trouble. The previous ICs that we have discussed would have never given you such trouble, but we had to live with low value of loop gain, and consequently somewhat it is going to become sensitive to supply voltage and temperature variations. Okay. So, we had just seen how a H feedback circuit starting from fundamentals could be converted into a useful IC with biasing etc. taken care of very well. So, that configuration that we have synthesized transforms itself into a very useful integrated circuit component, wherein externally we might have to do some amount of fiddling with it, okay, in order to make it work for the optimum bandwidth. Okay, this is an important thing. This is likely to be the tone set in hereafter, because we are going to use 2 stages and maybe 3 stages, and we are going to complicate our life further, right, and therefore practical design of these circuits become pretty complicated. Now, it does not mean that this kind of circuit can only be used in a differential configuration. If you are bent on it, you can also use single supply, okay, and no differential configuration if you take recourse to level shifting etc. This is another IC which is available. So, you can see that this particular IC here, a single supply is used and the bias voltage stabilization is achieved by using, now instead of the normal 1 resistor, okay, configuration, you might have to use, okay, 3 resistors just for biasing. Okay. So, you can see that this is another IC which is available, which uses no differential configuration, but straight away level shifting using a Zener diode. Okay. Earlier this was grounded AC wise, now you are putting a Zener diode. So, the collector potential of this is above the base potential. So, there is a small amount of reverse bias for this to operate. Okay. And we might as well add a common collector stage before giving feedback. So, do not imagine that this is necessary, right. If you want lower, still lower output impedance, okay, you can adopt this kind of technique, okay. And using additional transistor is not going to be a problem in integrated circuit. Okay. And in fact, you can bias this separately by putting another emitter resistance here, so that it operates at a higher current. Okay. So, I would like you to analyze this, find out the input impedance, output impedance, loop gain, okay, assuming finite beta for the transistors. Okay. Please do this as a homework problem. Is it clear? This is exactly similar to this structure, but using single supply. Now, what is the dual of this voltage controlled voltage source? Current controlled current source. What should be the kind of feedback now we have to apply? G. So, it is very simple to conceive of this configuration. Okay. Again we have the two stages cascaded. Now, it should be G feedback. It will be shunt at the input and series at the output. So, you have same thing RF, RE, but put this way, right. This should result in what? An ideal current controlled current source, or the parameter to be used here are for analysis G parameters. G parameters simply add, and the modified parameter is going to be H parameter, and it is H21 which gets stabilized or becomes wideband, and all the other H parameters will go towards 0 by the extent of the loop gain. So, all those things remain the same, and obviously what will be the gain? If this is the input current II and this is the output current I0, II will now completely flow through RF, very little of it will flow through the base. So, II will flow through this, and this will be resulting in a voltage which is II into RF, and what will be the voltage across RE therefore? II into RF, and therefore the current is going to be II into RF divided by RE flowing in this direction. So, I0 is going to be equal to II plus II, okay, plus II into RF by RE, or it is the same thing II, okay, into what? 1 plus RF by RE, which is the same expression that we had. Only thing is, since I0 we have assumed to be flowing in, okay, this is going to be negative. So, you can see therefore that this is going to be the gain of the stage. It has exactly identical method of analysis, except that the voltage and current change their role in this case. So, 1 plus RF over RE is the current gain in this case. Input impedance gets reduced considerably by the extent of the loop gain. Output impedance gets enhanced considerably by the extent of the loop gain, and the bandwidth improves by the loop gain. Okay. I would like you to again analyze this circuit using SPICE, okay, as well as normal method of analysis, that is G parameters, assuming finite betas for the transistors. Okay. So, these two configurations are the configurations which are cascaded configurations using two transistors. Now, can we go to the 3 transistor configuration? Now, by this time you must be totally aware of what should be done, right? It is a routine process now. What will be the feedback that will be, what are the feedbacks that are valid? Y and Z, valid negative feedback configurations. H and G will turn themselves into positive feedback configurations. okay, and therefore, again the problem will be the problem of frequency compensation is more severe in this case, because how many time constants are there? Minimum. Okay. There will be 4 time constants to deal with, which may be of the same order of magnitude, okay, and therefore, it will definitely go into oscillations. And we might have to therefore take care of frequency compensation of the same type, right, that we had discussed earlier. And that is what is done in the case of one of the popular, this is the ultimate thing, that is nobody has yet gone for 4-stage cascaded for wideband configuration. At 3 stages they had faced enough complications to stop and say we are now satisfied with the what? Loop gain, okay, and also consequent desensitization of the amplifier parameters with respect to the active device parameters. Okay. So, this is the point at which design of IC wideband amplifiers had stopped, okay, and that is simply 3-stage configuration. So, you can see this simply now cascade 3 stages. This discussion is equally well valid whether these are bipolar stages or FET stages. Okay. Okay, 3 stages cascaded like this. Then let us say what is adopted is Y or Z. Y feedback is pretty trivial because the arrangement is pretty simple. What is it? Connect the output to the base through RF. We can as well say the entire set of 3 stages can be now replaced by a single transistor and all this analysis. So, there is nothing brand new about this, okay, feedback technique, etc. Okay. So, a method of analysis is simple, use Y parameters, and therefore, the resulting configuration is going to turn itself into a current controlled voltage source, CCVS, ideal CCVS. Okay. The method of analysis is using by Y parameters, and the modified parameters are the Z parameters. Okay. And the forward transfer parameter of importance is Z21, and that is nothing but minus RF in this case. Okay. So, all those methods that we have adopted when we discuss single stage structure is valid here also. So, I am not going to discuss this. Instead, let us see the configuration, that is Z feedback, which is what is adopted in the IC MC 1553 wideband amplifier stage. So, we would like to feed the voltage in series and sense the output current now. So, sensing is done by this resistance and portion of it is fed back and converted into a voltage, and the voltage comes in series. So, you can see here this resistance, we will call it as RE1, this as RE2 and this as RF. Input is a voltage Vi and output is a current, right, I naught. So, we have now a voltage controlled current source. Let us quickly do the analysis here. to find out what? The admittance, okay, which is the one that is stabilized or wide banded, and therefore, let us evaluate that. Vi comes almost entirely across Re1, so results in a current of Vi by Re1. This current has to move totally through Rf, right, and therefore, the drop across this is what? Vi by Re1 into Rf, okay, plus Vi is the voltage across this Re2, and therefore, current through that is divided by Re2 okay, that is the current through this, and current through this is already known Vi by Re1. So, that is nothing but the total current, okay, and that is equal to I naught. Or I naught by Vi is nothing but 1 over Re1 plus 1 over Re2 plus Rf over Re1 Is that clear? The input impedance is increased, output impedance is increased by the extent of the loop gain, and the forward transfer admittance is stabilized and wide banded. And this particular thing is realized in the form of an IC here. Okay. Let us identify quickly. This is Re1, this is Re2, this is Rf. So, now you are aware of what this gain or the transfer admittance parameter is for this structure, and these are the 3 transistors which are cascaded together. Output is connected only through a common collector stage which is operating at a pretty high current. So, that output impedance, if you are taking it as a voltage, strictly speaking this is a current. This current is converted into a voltage by making it come across the 600 ohms, that is all, and that voltage comes as such at the output with low impedance. So, this portion of the circuit is for biasing. Using a single stage, you would like to bias this structure. So, how do you bias it? This configuration is left as such, because if it gives feedback for AC, it will give feedback for DC also, and therefore, it is its bias is going to be automatically getting stabilized. That we have to verify. So, as far as this is concerned, this is the bias current, which is going to be 6 volts minus 2 V gamma divided by 6K, it is about 0.8 milliamperes or so is the current flowing in this, and that is reflected here as the current. So, this current is almost totally reflected here, but this current is going to be very nearly equal to this current, because this is going to deliver only the base current. So, there is almost no DC drop across this. This resistance is put essentially for what? Isolating the input from the output. As far as biasing is concerned, there is a link of DC voltage through this, but we want to isolate the input and output. So, this resistance is put and it is bypassed by means of a external capacitor. This resistance is a large external capacitor. This terminal is brought out so that this capacitor can be put externally. So, this particular capacitor is to be put externally for bypassing this resistance. So, in which case, as far as AC picture is concerned, this will go out of picture. This is going to be pretty high resistance Okay. So, this will go out of picture. This current is essentially same as this current. So, if this is 0.8 milliampere, this also is 0.8 milliamperes, and therefore, what is the potential at this point? The base is at 0.6, let us suppose, from ground. What will be the potential of the collector here? You have to come back here, there is no potential drop here, there is V gamma here, there is very little drop across 100 ohms, because this current is going to be very small, that is what drop across this is very small, we say. So, this is roughly going to be 0.6. Okay. So, we know that this is 0.6 and there is going to be a drop of 3K into how much? 0.8, which is 2.4, and therefore, output voltage quiescent value is 3 volts, which is the center of 0 and 6 volts. So, that you can get fairly good output swing for this particular structure. So, you can see that this output quiescent is very nearly at 3 volts by this kind of arrangement here, okay. And you can evaluate the other DC voltages and DC currents. This voltage is 0.6, this is 6. So, you can find out the current in this, okay. And we know that this potential is, this is 3. So, this is 3.6. So, you know the current in this, and that is the same current as this. So, you know the drop in this, and therefore, you know the potential here, and therefore, you can find out the current in this. So, in any negative feedback structure like this, DC negative feedback structure, once you know the potential at one point, all the other potentials are going to be fixed with reference to that potential, because it is negative feedback, and that means the negative feedback configuration has bias points also almost completely stabilized. Okay. So, as far as frequency compensation is concerned, you can see this lead compensation here coming about, and there is a lag compensation put here. Okay. This is going to be resulting in some kind of dominant pole at this particular point, so that this lead compensation also can work well. Okay. So, we have a dominant pole introduced here by introducing additional capacitor here. So, again now you have to play with these two capacitors to achieve frequency stability. Now, again you see the amount of uncertainty involved. Okay. So, with this we are putting an end to our discussion about negative feedback wideband amplifier configurations. There are several other sort of structures which people have thought of. For example, there is a very interesting structure specifically used in a situation where you are interested in matching the input impedance as well as the matching the input impedance with the source impedance and matching the output impedance with the load impedance. In all these wideband structure that we have discussed so far, input impedance and output impedance will be increased by loop gain, and the loop gain is highly sensitive to supply voltage variation and temperature. Suppose we are bothered about gain being stabilized as well as input impedance and output impedance being stabilized in a situation where we require perfect matching. What should we do? So, what is done in such a situation is a very interesting configuration which is pretty complicated when you try to analyze it, okay, but looks very simple. So, let us see that configuration. These are the cascaded structures where I am going to give you G feedback as well as what? H feedback, both are combined. So, this is going to give you H feedback. So, RE1 RF, RE2 RF1, RF2. So, RC1, RC2. So, please analyze this circuit using SPICE, right. Please analyze the circuit first with what is that, alpha being assumed to be very close to 1. please analyze this circuit and find out the input impedance and output impedance and voltage gain and current gain for this. Both voltage gain and current gain are going to be stabilized. Apart from that, input impedance and output impedance will be stabilized, which can be made your 600 ohms or 50 ohms or whatever it is, depending upon the drive that you require. Okay? So, please analyze the structure using SPICE as well as your analytical tools. Okay. Thank you very much.